Our next speaker is Professor James Hartle from University of California at Santa Barbara. He's going to be telling us about quantum gravity and quantum cosmology.
Actually, I have to get out of this. Didn't escape. Here we go. And how does this alleged pointer work? Right?
Yeah.
He was having trouble with it.
You can just, everyone will see the pointer on all three screens.
Yeah, but if I move this, all I got is that hand. Well, that's good enough. Thank you very much. I'd like to begin with a key fact about general relativity. In Einstein's theory, gravity is the geometry of curved space-time. Mass and energy curve the space-time around the sun, for example, slightly. Free mass moves on straight paths in that curved space-time. That's the classical theory. But it has important implications for the quantum theory because it means that if you're going to construct a quantum theory of gravity, it's a quantum theory of space-time geometry that will assign probabilities to different space-time geometries, what their configurations are, given a quantum state. Right now, there are at least, two big theories of quantum gravity. There's loop quantum gravity, which is a non-perturbative effort to quantize classical general relativity using connections as variables and a mathematically precise construction of Hilbert space, and it's advanced quite far and has many predictions. There's also string theories, gravity unified with other forces in an essential way to make sense out of gravity in a multidimensional framework, and it's the dual formulations of the theories in lower dimensions on the boundaries of spacetimes. My understanding of the organizers is that they would like a review of these two theories in a half an hour. That's not going to be possible. So instead, I'm going to address the question of why are we doing this at all? What are the predictions? What are the outcomes? It seems unlikely that we're going to have a laboratory experiments that test any theory of quantum gravity in the immediate future. The scales, the natural scale, the Planck scale, constructed from h-bars C and G, is way too high. People argue over whether the scale be lower by modifying the theory, but we still have to face that dimensional number. So we are unlikely to have laboratory experiments, but we have one big experiment that we're in the middle of. In the beginning and the expansion of the universe, we have an experiment already done, where Planck energies were reached in the Big Bang, if you extrapolate general relativity back naively, and whereas the previous talk so ably illustrates, where there's a wealth of data today, scattered over a vast region of the horizon. That means the important thing for quantum gravity is actually quantum cosmology. How do we understand the entire universe in a quantum mechanical way? Now, I mentioned that the theory of quantum gravity would predict probabilities for different spacetimes. Most of our observations of the universe on cosmological scales, or at least some of them, are properties of its classical history. The homogeneity and isotropy we see on scales above 100 megaparsecs. The vast age of the universe, at least when measured in Planck units, of order 10 to the 60th. The rate of expansion, seen in the Hubble constant, the amounts of dark matter, dark energy, baryons, and radiation, all relics from a very early stage. And the evolution within the universe of quantum mechanical systems to make the CMB described in the previous talk, galaxies, stars, planets, biota, and even us. But classical behavior is not guaranteed in quantum mechanics. If, for example, you consider the orbit of the Earth around the Sun, according to quantum mechanics, there's a probability that it take any possible orbit. It's only in the particular state that the system is in, and the particular coarse graining with which we look at the orbit, that the probability is high that it moves on an orbit that conforms to Newton's laws of dynamics. So classical behavior is not general. It is an approximation to quantum mechanics that's appropriate in particular situations. But to compute quantum probabilities, it's not enough to have a theory of the dynamics like general relativity, or string theory, or even loop quantum gravity. You also need a quantum state, because in quantum mechanics, probabilities are basically the squares of operators applied to the quantum state. And of course, if we think, as we're assuming here, that the universe is a quantum mechanical system, then it has a quantum state. The question is, what is it? So a theory of the quantum state is an objective of quantum cosmology. The quantum state is not something we're going to measure. Our measurements are too puny to do that, and we've only got one system. Right? So a theory of the quantum state is, in fact, a necessary part of any final theory in addition to a theory of dynamics. So it happens that contemporary final theories have two parts. They have a theory of dynamics, which I've written here as H for Hamiltonian, and a theory of the state. So we can ask which regularities of the universe that we see come mostly from H and mostly from the state. We can also ask, a little bit later on, whether there's an unfinished task of unification here to provide one theory from which both would emerge. So here's a little list of regularities that we might expect of our universe that we might expect to emerge from mostly from H and mostly from the wave function. Of course, they all emerge from the combination. I'm just asking which is the most important. So certainly from the Hamiltonian, we get classical dynamics, the Einstein equations, for example, and we get predictions for laboratory experiments which are designed to be as independent as possible of any initial condition of the universe, for example, at CERN. But if we look on the larger scales, most of the regularities that we see probably follow mostly from the state. First, the existence of classical spacetime at all, as I have described on the previous stage, and the wide range of application of classical physics over, as far as we can tell, the entire visible horizon on certain scales from a short time after the Big Bang to the infinite future. Then the particular properties of the state, the early homogeneity and isotropy now on scales above homogeneity, 100 megaparsecs and so. Inflation, if there was. And the fluctuations away from these symmetries that we see in the CMB today and in galaxy and the large-scale structure of the galaxies later on in the universe. Arrows of time, if the dynamical theory is time reversal invariant, as all our best candidates are, then to explain the arrow of time, you have to say something about the quantum state. The CMB, the large-scale structure I've already mentioned, the existence of isolated systems. We're all semi-isolated systems in this room, but that's not guaranteed in the theory in any sense. It's a property of, and there were none in the very early universe. They emerged. The topology of space-time, right? Whether it might be, for example, something like a torus or a hall of mirrors or something like that, or an iosphere. the number of large and small dimensions in a theory that has those, the number of time dimensions, for example, coupling constants of effective theories. There's a huge list of things we might hope to get out of the state. I'm going to report very briefly about those. So to do that, I'm going to give you a very quick introduction to wave functions of the universe, which represent quantum states, in a very simple class of models. Models which are homogeneous and isotropic, and therefore have, whoops. There we go. All right, therefore have only one quantity, which is, so they're like spheres, and A, for example, is a scale factor that represents the overall size of the universe at any one time. Now, in ordinary quantum mechanics, wave functions are functions of x and t, and you can think of those as the quantities, if you have a history, x of t, they tell you what, they specify the history on one space-like surface. In quantum gravity, we also have histories. Here's, for example, a history of the expansion of an expanding and collapsing universe, described by the scale factor A, which is a function of time. And if we have a scalar field in addition to the geometry, it's usually argued that the wave, you don't need an additional time variable, right, to label which point you are, because the size of the universe itself tells you where you are in this curve. So wave functions in a very simple model would be a function of scale factor and one field, let's say, for example, scalar field. It's important to stress that wave functions of the universe are not an initial condition, because initial and final already presume that you have a notion of space-time, and we're seeking to produce the notion of classical space-time. So you have to think of them in four-dimensional senses as representing something that will tell you what went on in a four-dimensional way, what went on then, what goes on now, and what will go on in the future. And that way it becomes predictive. Now I'm going to report on one particular state, right, which is Hawking's no boundary of the wave function of the universe, only because that's been the most developed. This wave function is the analog for closed cosmologies, right, of the ground state in ordinary field theory. And since there's plenty of evidence, the ground states typically are very simple, and the early universe was very simple, more homogeneous, more isotropic, more nearly in thermal equilibrium, that might be a good candidate for the quantum state, theoretically based and, you know, in rough connection with observations. But you can't, in a closed cosmology, think of a ground state as being the lowest eigenfunction of some Hamiltonian, because from the diffeomorphism invariance of general relativity, the closed cosmology, the Hamiltonian vanishes identically. Also, everything is an eigenstate of it. But in ordinary field theory, there is another way of constructing the bound state by a Euclidean sum over all histories that match the arguments of the wave function. And so we can construct a state which is the Euclidean sum over all four-dimensional geometries that have one boundary, right, where the arguments of the wave function, this is supposed to be a four-dimensional geometry, scale factor, four-dimensional scalar field, matching a three geometry and a three-dimensional scalar field, and we just do an integral over e to the minus the action of the theory, and we produce a wave function which is the analog of the ground state, and that is the candidate I'll discuss for a wave function of the universe. So first of all, how do we predict that there's any classical space-time at all? This integral, which I showed you on the previous slide, imagine it doing by steepest descents. Then you, basically, the result will get e to the minus times the extrema of the action. And the no-boundary wave function, therefore, predicts something like this. Since the extrema are generally complex, I've tried to draw a picture of one here, right? Here's the one boundary where the wave function is defined, and that's the no other boundary. And this is complex. We call them fuzzy instantons, but there's no particular reason for that. At any rate, the state would have this form, and it will have a real part and an imaginary part to the action. But that should look familiar to you. It's ordinary WKB. And so we predict an ensemble of classical spacetimes, which are the integral curves of the imaginary part of the action here. That is, the solutions to the Hamilton-Jacobi equations, momenta equals the gradient of S, and the probability is roughly the square of the wave function, which is e to the minus 2IR. So thus, we've predicted an ensemble of possible classical spacetimes for what the universe might be like, with probabilities for what they are. And not all classical spacetimes are predicted. Whoops. So let's just give one simple example. Ask the question, does the no-boundary wave function predict high probabilities for inflation in the early universe? The answer is no, it does not. By itself, it predicts all early histories inflate, but the probability for the number of efolds, roughly here, is declining. But in cosmology, you have to take into effect that everything is inside, including us as observers, which are also quantum mechanical systems in the universe. So the theory may predict probabilities for what occurs, but it's a different set of probabilities for what we would observe, because we're particular systems and we only have a probability to exist in any one Hubble volume. It's more probable that we exist in larger universes because there are more places for us to be predicted. And that means that even though the probability for inflation to occur with a large number of efolds is small, the probabilities for us to observe a lot of inflation by our observations is actually high. Thus, the theory agrees with the experiment. Well, that's homogeneous and isotropic. Of course, it's standard perturbation theory to extend that by considering little fluctuations, right? That's a typical graduate student problem. We did the homogeneous isotropic part. Now you can expand in fluctuations and calculate that. Since the no-boundary wave function is essentially a Euclidean construction, right, it won't surprise you that the fluctuations start essentially in their ground state, something called the Bunch-Davis vacuum. And if you know the technology of that, where these are the standard slow roll parameters, and these are the size of the fluctuations, they give you the standard prediction that's usually assumed in cosmology to explain the scale-free invariant spectrum or something that we see in large scales. So this works pretty well also. In short, the wave function predicts probabilities for different CMB maps, as we saw in the different, as in the preceding talk. Arrows of time. Well, our universe exhibits a number of arrows of time. So the fluctuation arrow. The fluctuations seem to be small in the beginning and grow as it goes on. There's the thermodynamic arrow, the growth of entropy, right, in the universe. The radiation arrow, the retardation of electromagnetic radiation, and the psychological arrow that we order prediction into past, present, and future. These arrows are all, I don't have time to go into it, but they're all essentially the same. They follow from the fluctuation arrow. And they can be explained by this special quantum state, like the no-boundary wave function, where the dynamical laws are time symmetric, right? But the state of the fields is different in different geometries. So, no-boundary wave functions vanish at one and only one place on the instanton, down here from symmetry. This means the fluctuations, turns out to mean the fluctuations are small only at one place in the universe, which is, if we only have an expanding universe, would be at the beginning. But an interesting example is, what if we have a bouncing universe, right, that contracts and then re-expands? It turns out the fluctuations are not small at one end, large end, or the other. They're small in the middle. That means the arrow of times, all the arrows of time, will point in opposite direction on opposite sides of the bounce in a symmetric way, right? Even though there's an arrow in each place. That's not very good for getting observational information about the other side of the bounds, because people back here will have had about as much chance of sending us information as we have sending information backward in time to tell people not to vote a certain way in an election. It's not going to be done. Well, I had a big list there, which I'll go over again, but there are some of the successes, but there are some things that are interesting that we just haven't been able to do yet. A space-time, geometrically or mathematically, is a manifold with a metric on it. A manifold is just the topological structure of the geometry. So, for example, you can imagine manifolds like a sphere, or have a handle on them, as in these fanciful pictures on the side, or like a donut and so forth. If we seek to predict the classical metric, we might also seek to predict probabilities for what manifolds we have. And that has an observable effect if it's not on too large a scale. That is, imagine, for example, the universe was like a torus, or one of these halls of mirrors you see, where you see infinite reflections going off in different directions. That would have an effect on distorting the CMB that we observe, because you'd see one reflection of it, another reflection of it, another reflection of it, if it wasn't on too huge a scale. So large-scale topology, at some level, is detectable by its effects on the CMB, and that's been looked for, and so far there are no effects. But it's a very hard problem to do, because I showed you how saddle points led to a very simple universe, but we have very little information about what kind of saddle points, complex saddle points, would exist on manifolds with complex topology. But if we had them, then we could actually compute. So, where are we on our scorecard? The features we might expect to be predicted, or here's the list I had in the beginning. Classical spacetime, yes, the theory does predict that the spacetime is classical, and moreover, what the classical spacetimes on very large scales are. Early homogeneity and isotropy with inflation, yes, it predicts that through the fluctuations. Fluctuations start in their ground state, yes. Arrows of time, it certainly predicts the arrows of time as a special state in a time-symmetric theoretical framework. The CMB large-scale structure, there are a lot of things I didn't say here. Isolated systems, for example, the separation of the Planck scale, the remarkable and very lucky fact that we didn't have to know anything about quantum gravity to do the rest of physics, right? We only have to know about it in extreme circumstances. Topology of space-time, number of large and small dimensions in principal predictor, et cetera. So, some successes, I've only been able to report on a few. That's quantum cosmology. But in this centenary year, it's maybe appropriate to think about general relativity in a broader context. Robert Oppenheimer, writing a eulogy in Reviews of Modern Physics, I think, in 1956, right after Einstein's death, was kind of critical of general relativity. He said in the 40 years that have elapsed since the classic initial test what he means, these have remained, the deflection of light, the precession of the perihelion, the gravitational redshift, and so forth. These have remained the principal, and with one exception, the only connection between general relativity and experience. I think the implication is that the theory had been, in some sense, a failure. And indeed, if you make a plot, a convenient plot that I learned from Clifford Will, of the mass of objects measured in grams going up this way. I apologize for the low quality of the graphics here, versus their size in centimeters. Then, roughly speaking, relativity is important when the ratio gm over rc squared is approximately 1, that is, lying along this line here. Can't be bigger than 1 because you're inside black holes, but the further phenomena are closer to the line, then the more relativistic effects are important. So the present universe, in some approximate way, runs along this line from the Planck scale way down here all the way up to the present. And the sun, no, it's an order 10 to the minus fifth effect, is somewhat close to the line, and that's the way it looked in 1956. Oops. Yeah. Today, it looks better astrophysically. There are a lot of things. There's the quantum gravity scale down here, the end of inflation. So, we have pretty good evidence for some sort of inflation occurring. Primordial black hole evaporating today, which we haven't seen yet in the diffuse X-ray background. And many more tests of the theory of relativity on solar system scales, remarkably accurate one, for example, the test of the bending or the Shapiro time delay by the Cassini mission to a part in 10 to the fifth. That was unheard of, certainly. Neutron stars, properties of neutron stars, maximum masses, and so forth. And the global positioning system, as Cliff stressed for you the other day, would fail in a half an hour if it didn't compensate for the effects of general relativity. Black holes and galaxies we have, and of course there's the present universe. So it's much better today. But if you're interested not in just what's going on today, but where did all this stuff come from, right? Then GR, first of all, is the key, as I've already mentioned, to the existence of the quasi-classical realm, to the utility of classical physics, and it's central to the origin and properties of today's isolated systems. So if you're working in a laboratory and you trace back, right, where we are, you're talking about a curve that started out here from the Planck scale, came up, then the fluctuations grew under the action of the quantum fluctuations grew under the action of gravitational attraction to collapse, eventually to make galaxies, stars, planets, very small fluctuations, us, and doing experiments in laboratories. So if you're interested at all in history, you're interested in general relativity, both classical and quantum. So in 1956, it looked like this. But in the future, it may look more like this. There's increasing evidence that gravity might be, in some sense, a theory of everything, right? Where everything is affected by general relativity, going backward. So a century after its inception, Einstein's general relativity is central to physics, both on the frontier of the very large and also the frontiers of the very small. Martin Seligman, who was president of the American Psychiatric Association, was the subject of a CNN special, and they said to him, well, what we're interested in is the state of American psychiatry today. So, but we had to be short. How would you summarize that in one word? And he said, good. And then they said, well, that's not very informative. How about 2 words? And he said, not good. They said, well, you just contradicted yourself. So how about 3 words? And he said, not good enough. And ladies and gentlemen, if I had to summarize for you in 1 word, 2 words, 3 words, and 4 words, the state of quantum gravity and quantum cosmology today, it would be exactly that. It's good. Amazing progress has been made. A lot of questions that we never asked before have been addressed and are keeping on being addressed. It's not good, right? Because we're quite far from any having definitive resolution. There are a lot of puzzles like black hole evaporation that are confusing. In short, It's good, but it's not yet good enough. Thank you.
Energy was 10 to the exponent 28 electron volts. And yet, the donut-shaped singularity that generated the Big Bang, that had an energy of 10 to the exponent 90 electron volts. Does that mean that quantum mechanics is invalid in those regions because the energy of the Big Bang is 10 to the exponent 60 times greater than the largest energy of that Planck cube?
If I had more time, I agree with your question, right? How do we know quantum mechanics applies to the universe as a whole? No, we don't. The biggest laboratory experiments, like Friedman et al. On Josephson junctions, only go up to 10 to the 8, well, there's some dispute in condensed matter physics particles. So we only had the theories only tested on laboratory scales. What's the justification for extrapolating it to these very large scales? First of all, it seems to work. For example, on the story about the quantum fluctuations generating large-scale structure. But frankly, we'll only find out whether it applies if we do it and then see if there's some horizon. Right. Thank you.
I wonder if there's some anthropomorphic hypothesis in your work.
Anthropomorphic?
You said that there's inflation could have happened because there's more space for us.
Mm-hmm.
So in your model, does that mean that is it necessary or sufficient for there to be inflation for there to be people?
I don't think we know anything like necessary and sufficient because we only have one universe to study. But you're right. Anthropic reasoning, so-called, that people did a long time ago is automatic in quantum cosmology because all of our observations are contingent, as Bohr said, right, on a description of the observational situation. For example, it doesn't make any sense to say, what do you predict for the temperature of the microwave background? Because it varies in time and it depends on what time it is. So you have to put that kind of information, a description of the observational situation in, including us. So that means that we won't observe what is where we cannot exist. So imagine, as in contemporary landscape theories, the cosmological constant varies from place to place in the universe. And its typical value is of order 1 in Planck units, not 10 to the minus 122 as it is in our case. We wouldn't observe 1 because a large cosmological constant, as Weinberg, Barrow, Tipler, and other people showed, that's only a little bit larger would mean the universe would expand so rapidly that galaxies wouldn't form. So if you calculate the probabilities for what occurs, it might be very large, but the probability of what we will see is very small, and those calculations give you a number which is, with plenty of assumptions, give you a number which is essentially the largest it could be and still be consistent with galaxy formation by 13 gigayears, that is, given the age of the universe. So yes, we can do that.
Thank you. Last question.
If I'd known I was going to be 6 minutes over, under, I would have discussed it.
Okay, here is another question. Everyone in this room can solve the following problem. In the early ultra-relativistic universe, and if we assume a number of fermion degrees of freedom and boson degrees of freedom, we can calculate with the Planck distribution how many particles are within a unit of volume, and we can calculate the distance to the horizon. So then we know how many particles are within the horizon, and at the Planck time, the answer is less than 1 if the number of fermion and boson degrees of freedom is not much larger than 100. So if at the Planck time, you have less than one particle within the horizon, a quantum effect of gravity that could have changed interactions had not yet occurred. So is gravity quantum or classical? I think nature never answered that question. Can you comment on that?
In all the work described here, right, I'm assuming that everything is quantum. And the usual story is quite different from what you said, that all the matter is made as we roll down in some inflationary potential at reheating, which is a much later stage. So you don't get to extrapolate the number of particles all the way back to the Planck scale. There aren't any, right? And even the notion isn't correct. So, but I'm assuming quantum mechanics because that's what we know. Whether that holds on these scales, as I've just mentioned, that's a very interesting question, and we'll find out by doing it.
Thank you. Let's thank the speaker again.